All right. Hey, everybody. My name is Ara Bernardi. I'm with the VDI team at Microsoft, and this is a talk about VDI, architecting VDI for scale and performance. 5 o'clock is not the best spot for this kind of talk because I'm going to throw a lot of data at you guys, but I'm hoping I can make it relevant. So you can look at, when the talk ends, or you look at the slides and you look at this recording again, look at it as a blueprint with lots of data you can use to design your own architecture. Okay? If I had my way, it would be at 8:30 a.m., but this is the slide I got. So what I'll do is a quick intro to VDI in 2012. How many of you guys are familiar with 2012 VDI? Like played with it, deployed a little bit, you know what it's looked like? Not many. All right, so I'll spend some time talking about how to deploy it, what are the basic components, and what the general flow looks like. Then after that, we'll do a design of large-scale architecture, and we'll go through multiple variations, like pool VMs and PD VMs. And then while we're doing that, I'm going to talk about what are the system requirements for delivering that type of performance. And then at the end, which is about the second half of the talk, I'm going to share actual test results, charts, and so forth. With that, quick intro to VDI 2012. These are the building blocks in a LAN environment. On the right-hand side, we have personal desktops, pool desktops that use user profile disks for storing user settings, or RDSH, the traditional TS, session hosts for high-density sessions. We call that VDI, even though this talk is going to focus on pool VMs and PD VMs. The heart of the system, the management system, is the RD connection broker, which is on the top. And we use a SQL Server backend for all the configuration data and the dynamic settings, like where user might have a disconnected session when they reconnect. And RD Web is a web service where user logs in to see the applications published to them, and is really the front end to the users. So let's do a quick walkthrough. User on a LAN environment, this is within your CorpNet, connects to the web services, logs in at the web server, and our RD Web service contacts the remote desktop connection broker with the token from this user and says, what are the applications and collaterals and collections published to this user? And populates a web page with these icons where user can connect and start accessing that collateral. So then the user clicks on one of these icons, a publish app, it might be IE, it might be Word, whatever, and RDP starts, and RDP connects to the connection broker again. This is just an RDP path. Connection broker authenticates the user and says, aha, you have a connection somewhere else, or you have a session, or there's a publish app for you somewhere else, and sends a blob back to the user. So after authentication, the RDP connection is live, and there's a blob sent back to the RDP client for the best target. And then RDP client silently uses that blob to connect again and seamlessly logs in into whatever the final target was, because the RD connection broker in that blob has got authentication information and has got user's password encrypted, already sent to the target, waiting for the user to connect, and it expires within a minute. So it's a secure way of providing a single sign-on for the target, because user already had to sign once when it hit the connection broker. So that's the LAN environment in a nutshell. If you have users who are coming from internet, there's a firewall, and there's, again, an RD Web service sitting at the edge, and RD Gateway, which is our firewall for RDP. It only allows RDP traffic, and it's wrapped under HTTPS. Okay? So here, user again connects to the RD Web. It's an HTTPS connection. Logs in. There's the edge server has got two networks, right? The WAN network and a DMZ network. It connects to the RD connection broker, and RD connection broker gets all the information, collects all the information for this user, sends it to the web server. The web page displays all the icons, which are resources published to this user. User clicks on one of these collaterals, and RDP starts on the user side. RDP starts and uses that information to go now through the gateway. The gateway acts as a proxy. It has policies also, and reroutes the connection to the RD broker just like before. RD broker authenticates the user, looks up where the user should go, and sends back a routing information for the best target. The blob gets back to the user on the LAN, and RDP client seamlessly restarts a new connection with the blob information, hits the gateway again. Gateway does the proxy stuff and sends it to the right target. This is overall what the components we have as part of Server 2012 VDI and how the connection flows in Server 2012. As I mentioned, we really have three collaterals in this VDI spectrum. It's the sessions, which are the traditional terminal server, pooled VMs, which are a collection of VMs that share the same gold VM or parent VM, and personal VMs, which are just like desktops. They're given to you, dedicated to you, you become the admin on those. The most cost-effective solution is session-based because many users, hundreds of users, share the same image. One single operating system is shared by 100 users. So updating that one image means 100 users, the runtime environment for 100 users got updated. And that has the lowest cost, in effect, because of this ease of management and shared environment. App compatibility, well, it's running server SKU. So some vendors only certify applications to run on client SKU, so there's a little bit of app compatibility issue. Users, because they're in a shared environment, cannot be admins, so there's a limit to how far they can personalize the Windows runtime environment. They can only personalize what's in their environment, their settings, and so forth, but cannot affect machine state. So some applications may require, like if you're a developer, you're developing code, you might need something that affects the machine configuration. That's not going to work on RDSH because you can't be an admin. Next is the pooled VM, where it's a client SKU that you're running. It is a bit more complicated to manage, but from a single template, we generate, this is the parent gold VM, we generate all the child VMs. So there's a bit of a common image management here that also is relevant for pooled VM. But it has the best app compatibility because applications running on pooled VM, they're running really on client SKU. So any application that was certified for Windows client will run in this environment, right? But because it's a pool environment, pool VMs, it's a shared environment in the sense that when the user logs off, we reset the pool VM to the original clean state, so user cannot make changes to the system. So users can't be admin, even if they were, their changes will be thrown away. So there's a limit how far you can personalize that environment. Just like RDSH sessions, you can personalize your environment, your runtime environment, but not the system environment. And the one on the right is personal VM, which is like a desktop, your laptop. You own it, you're admin on it, and it's managed just like the desktop. So ease of management is not there. You have to individually manage these VMs, but you can be admin on it, you're a developer, whatever you want to do over that machine is like having your desktop and you can manage. This session is focused on the pool VMs and personal VMs. I'm not going to talk about RDSH, which are the session hosts. But I just want to throw it out there that that gives you the best density with those drawbacks. And the slide, I think it's a good way of describing the spectrum of benefits and drawbacks of these three solutions. All right, let's design a VDI, a large-scale VDI for performance. But before we do that, let's consider some parameters here. Some activities are very expensive, like provisioning, updates, and boot phase. Provisioning is when you say, I'm going to create a new collection from this gold VM I have. We have to create every VM, and that's very high in I/O, and some CPU. Login phase also can be very expensive because if you want everybody to log in the first 5 minutes, say you have a shift workers, 8 hours, they come in at 8, they have to log in within 8:05, and then the 5 o'clock shift comes in, so the 8 o'clock shift has to log off so that the 5 p.m. shift has to come in. That's very intensive in I/O also. But what really matters is that once users logged on in that 8-hour, 10-hour shift, how is the performance of the system? And that's what we try to model, try to estimate, try to simulate, and draw conclusions about the requirements of the system throughout the day where users are running their workload. So system load varies also by usage pattern. Task workers don't put as much load on the system, whereas power users do. The benchmarking we use, any benchmarking, is really a simulation. We don't, a real world run might demand more, so it's important to do an estimation of or a characterization of what does the typical load look like for particular user groups you guys are thinking of deploying VDI. And you can use what I have as a blueprint for a reference workload we have. And the best strategy is really to try small deployment, see what the workload looks like, and then build on top of that. Speaking of simulation, the tool we used for all the data that I'm going to share with you is based on this product called VSI from Logging Consultants. It's VSI 3.7 medium workload with Flash. And in a 12-minute period phase, it's kind of hard to read, but basically they go through, this simulation goes through about 12 or so applications, brings up open dialog, runs scripts, types into Outlook, basically exercises the system trying to simulate a typical knowledge worker playing video. And within that 12 minutes, they sample what the response time is for how fast the windows come up or how fast the buttons respond to clicks and so forth, and come up with an estimation of overall response time. There's some number above which the response time is visibly too slow for interactive users, and you say, well, that's the cutoff point. Beyond that, the system cannot support interactive users that would be satisfied, right? And Login VSI guys also have a booth here. If you guys want to try it out, I think they have samples. You can get cards for 200 user type samples and try it for a few months to see how you like it. This is what we used. Internally, we have our own performance modeling system, which is similar. And the funny thing is that our results look practically identical, even though it's a different infrastructure, and we draw our patterns from results we get through, say, Office customer usage, so we know how often, so for example, Office users click on this and that, and we put it in our simulation. Results are practically the same in terms of scale and density, I/O load, network load. They're practically identical. Just that VSI has become a benchmark, a standard benchmark, so we're using this when we're communicating this openly so that people can refer to benchmarking results from other vendors and make a comparison. All right, so let's do a 5,000 seat deployment. We'll do a walkthrough, 80% on LAN, 20% from WAN. We'll explore design options, and we'll talk about scale performance, requirements for design, and how to optimize things. First, we need the VDI management, the VDI management servers. These are the backend services that create VDI and facilitate the VDI deployment. We have, remember from the intro slides, we have the gateway, RD web access. We need the RD license server, the RD broker, and SQL server. These are typically you would have two hypervisors that are optionally clustered. I say optionally clustered because our services, we have application level high availability. So if one goes down, there are two running together. They're doing load balancing. If one goes down, the other one can't take the load. But optionally, you can cluster two. SQL has got several models for HA, and one of them does require clustering of the hypervisors. So this would be up to you. But the key point is that you have two hypervisors and an HA deployment of the services required to have a VDI deployment. For this to be a clustered environment, you would have a shared storage. And the shared storage would be a scale-out file server and multiple networks, WAN-facing network, because remember that for WAN users, we'll have a web server and RD gateway that is facing the internet, and of course the LAN for the back end. Now, the servers we used were our 720, which has got a E5-2690 class of Xeon processors. And the relevance of that is because each item I'm describing, I'll note how many cores you need. So you can do the mental translation or back of the envelope translation. How much CPU do I need for this kind of workload? So the RD gateway, we measured it can handle 1,000 connections per second per RD gateway. Remember, you have 2 for HA, so typically they will do only 500. The 1,000 connections, they generate about 60 kilobytes per second. That's the network traffic due to RDP that we measured when running the VSI medium workload, right, with Flash. And this configuration was 4 cores and 8 gig of RAM. The hypervisor had 16. The RD broker can handle 5,000 connections in less than 5 minutes. It depends how large the collections are. You need a minimum of 2 RD brokers to have a high availability configuration. Some test results to share with you. 50 concurrent connections are routed in 2.1 seconds against a collection of 1,000 VMs. So that says in 2.1 seconds, we were able to log in the user at the broker, figure out where the user should go to, and send a routing blob back to RDP so that the user now would go to the final target and log in. The broker doesn't do much work when there's a SQL backend, so that's why 1 core and few gigs of RAM is sufficient for the broker. The load on the SQL server is not that much either. I'll share with you the CPU and memory and IOPS load, but in terms of just the static data, our database is small, 60 meg for 5,000 seat deployment. Creating a VM, which is the phase of provisioning, is transaction heavy, 1,100 transactions for 100 VMs. User connection is transaction heavy, 222 transactions per user. You have 5,000 users logging in. You can imagine the number of transactions. But again, the load on the SQL Server is pretty low, and I'll show that near the end. This configuration, 4 cores with 8 gig was sufficient. Tweaks and optimizations. In 2012, we have a PowerShell interface, and one of the options in PowerShell interface is to increase how many VMs we provision concurrently. And in 2012, the limit was 5. The bottleneck is I/O. So your storage should be able to handle more, and if it can, then this will cut down the amount of time it takes to provision VMs or update VMs. In 2012, R2, and we're still testing stuff and still debugging stuff, we hope to have a max limit greater than 20. We have tested it at 20, and the provisioning time would be about 5 times faster. Next, now that we have the VDI management services, we can move to actual VDI deployments. We'll consider pool-only VM with local storage. So hypervisor and storage together, towers of CPU and storage, CPU and storage, CPU and storage. Next one would be hypervisor, just CPU, and centralized storage for storing all the VMs. And the final will be a collection of pool and PD VMs. Let's do the pool VMs, local storage. So in this configuration, you have the hypervisors on the right side, 5,000 seats. You need maybe 30, 40 hypervisors. We'll get to do the numbers next. But in this configuration, all the pool VMs are running from local storage. So there are 10 15K disks and 2 15K disks for the OS. And because these are pool VMs, they don't need to be clustered. If one of the hypervisors goes down, no big deal. User connects to another hypervisor. Another identical pool VM is created for the user, and all the user's environment settings come either from the user VHD or the old traditional roaming user profile or the user environment virtualization. So VMs are not special. Hypervisor dies, no big deal. Another VM would be just as good, right? But user settings have to be on an HA storage. That's why on the left-hand side, we have the scale-out file server and shared storage across 2 SMBs. So there's high availability for all the user settings and user documents and whatnot. So the CPU usage on this class of server, R720, which is the E5-2690 Xeon 16 processor cores, 150 medium with flash VSI workload at 80% CPU. That says about 10 users per core. And the reason we're talking about 80% CPU is because this is a simulation. And you want to put some headroom to make it relevant to real world type of environment. There's going to be glitches. There are going to be some users who use more flash or whatnot. So we felt, well, 80% is about reasonable, 20% headroom, 150 users, that's 10 users per core. Each Win8 VM with Office 2013 uses no more than 1 gig of memory, so 192 gig is plenty of memory. The RDP traffic running VSI medium workload is about 500 kilobits per second. And that says for 5,000 users, you have about 2.5 gigabits of load on your network. That'll be a load coming to your data center if you have consolidated all your hypervisors in a data center. But if you have spread out your hypervisors in different buildings or different places, it's just a switch to those hypervisors that have to take number of users for those hypervisors. The load on the WAN would be about 500 kilobits, not bad. And that's the RDP traffic on your network. There's no storage traffic on the network beyond the roaming profile and the user VHD. Now let's look at the load on the local storage. The VSI medium workload generates about 10 IOPS per user. You have 150 users. And because this is a pool VM deployment, all the VMs are reading stuff from their gold VM, the parent VM. So about half the load is going to the gold VM. That's about 700 reads per second. You see in the chart, gold VM has got the highest read. Then to the diff disk, which is per VM, we see about 400 writes per second and about 150 reads per second. And the user VHD, which is user settings, that's about 2 IOPS per user. And that says per hypervisor, that's about 300 writes per second. Even if you use the roaming profile, you would be caching the roaming profile locally, and equivalently, you would have the same 300 IOPS per second go to your local cache. So gold VM and diff disks are local on the storage. The local storage is supposed to do about 850 reads per second and 400 writes per second. The array I described to you guys, 10, 15K disks, handles this load just beautifully. And we can drive it even further, and I have data to share about how far you can drive this infrastructure. In terms of size, each collection has a gold VM. Gold VMs are about 20 gig. Each diff disk is about 5 gig. So you say, well, each hypervisor is going to handle multiple collections. So altogether, several terabytes local storage is plenty. So back to the user VHD. So user VHD is running off of centralized storage. It's about 2 IOPS per user VHD. That says your centralized storage should be able to handle 10,000 IOPS for 5,000 users. It's write heavy, and that's a significant load. In terms of amount of data, it's not that bad. It's about 100 kilobits per user, which means the load on your storage network is tiny, half a gigabits per second. Tiny, relevant to how large network load can be in a storage data center. Storage size for the user settings, we think about 10 gig per user is reasonable. That says about 50 terabytes of storage. And the overall load on the network, if you don't have a data center, it's a mix of half a gig for the user settings and 2.5 gigs for the RDP. If you do have a dedicated data center, obviously the storage traffic is in the data center, doesn't spill out. So the load on your network outside of data center is just the RDP load. Tweaks and optimizations. So SSDs are very helpful on the gold VM because the gold VM is shared across all the pool VM instances. And the average reduction on the IOPS is about 45%. Very big. And so one option is what we have here, which I described, 10 15K spindle disks. The other option is you can use an SSD, 2 SSDs, RAID 1, to put the gold VM on, and use only 4 15K RAID 10 disks. The benefits are that the SSDs provide substantially faster read performance, and that would help you when you're doing booting login time. Remember I said if the login time is tight, the load on the storage is high, that's when you definitely want to consider SSDs. If you have a more powerful server that can host a few hundred users, 300, 400, 500 users, then you're going to run out of spindles for local storage. You have to switch to SSDs. Next, let's look at what happens when we put a pool VM deployment using on a centralized storage. So in this deployment, you see the hypervisors do not have local storage. The two 15K disks are just for the operating system. And all the VMs are running from a centralized storage. Again, the hypervisors are not clusters because we're talking about pool VM. One hypervisor goes down, no big deal. You log into another hypervisor, you get the same pool VM. And after login, it's specialized by pulling in your user environment. Everything is running off the SMB scale-out server, which means user VHDs on that server, VM VHDs are there, and gold VMs are there too. The CPU, memory, and RDP load is the same as before. Nothing has changed, right? So we'll jump over to the SMB storage. The SMB storage, the load is really the load due to the 5,000 users. So you had 50,000 IOPS before, which were distributed across these hypervisors with local storage. Now you have the same 50,000 IOPS as before, but now they're centralized, right? They're aggregated on two SMB scale-out server with a shared storage behind them. The pattern is the same, it's just the magnitude is different. Same 50,000 IOPS, right? Gold VMs again, take the highest amount of IOPS, read IOPS, right? About 22,000. Then the diff disks are the second. And there's a lot of writes going to the diff disk and finally the user VHD. In terms of sizing, it's similar, just aggregated to a central location. About 20 gigs per VM for a collection. So a terabyte can handle about 50 collections for you. Diff disks, you have 5,000 of this, so 25 terabytes. And the biggest one is user environment, profile, folders, documents, and so forth. That's 50 terabyte if you assume each user has got 10 gigs of storage. Overall traffic, though, is very different now, right? Because everything is running off of the SMB storage. Now the network traffic, the storage network traffic is huge, is 30 gigabits per second, right? So it should have a data center for this and isolate the network from the public network where the RDP LAN traffic is. And for 30 gigs, you want a high available network, which means two 40 gig networks. Significant amount of load on your network. So then you say, why am I doing this? Because I made my storage network more complicated. And what's the benefit of this? Well, the benefit is that if you have a centralized storage, one of the features in SMB is this thing called CSV block caching. And CSV block caching basically keeps in memory, in SMB server's memory, all the hot blocks. So it reduces the load on your storage. So effectively, you can have the same deployment with a lower cost storage. So let's say you had a storage that could handle only 4,000 users. You can have 20% more users, 5,000 users, once you enable CSV block caching. Okay? Just important to note that block caching is per collection or per gold VM. And so if you have 100 collections, you need about a gig per collection to have this benefit. And the benefit, as I said, is higher VM scale per storage, right? 20% more once you enable CSV block caching. Your storage requirement just dropped from the 50,000 IOPS aggregated. Remember when we had distributed hypervisors with storage, each had its own equivalent, you could handle 50,000 IOPS. Now, centralized, you can support the same number of users only at 30,000 IOPS. Okay? Benefits, because CSV cache is basically RAM cache, right? You get faster boot time, faster login time, and faster creation and patching. The cost is data center network for your storage. Then there's the SSDs for gold VMs. SSDs also reduce the IOPS by about 45%. So you say, well, what's the difference between SSDs and CSV block caching? Well, CSV block caching is using the memory of the server For 100 collections, you need 100 gig per server. If you're running out of memory on the server, you throw in the SSD. That would complement what the block caching was doing for you. Benefits are just like before. Faster login time, faster boot time. As far as tweaks go, in 2012, you would have for 5,000 users, maybe 30 or so hypervisors, and you want to balance the traffic from these hypervisors to the SMB scale-out you have, 2 SMB scale-out servers or 4. And there's a PowerShell script that interface that allows you to set SMB clients or affinity between SMB clients and SMB scale-out servers. In 2012, that's done automatically, so you don't have to set this up, and just optimize this, load it across the SMB scale-out servers. Next, let's do a 5,000 seat mix of pool and PD VMs. So here we have a mix of PDs and pools, and it's important to cluster your hypervisors because PDs are dedicated to the user, and if the hypervisor goes down, user can't connect to any other VM. He has to connect to his own VM. So PDs must be highly available. That means a shared clustered environment. Not only your storage has to be highly available, but your hypervisors have to be in that mode too. Fortunately, in 2012, we can handle 8,000 HA objects and 5,000 VMs. That says you're well within the margin of our 8,000 HA objects. Only PDs need to be in HA mode. By default, we throw everything in HA mode because it's a cluster server. But if you had to, you could use a PowerShell script to tweak it such that only the PDs are HA. And you can assign priority to PDs also. So if a hypervisor goes down, the PDs get started first. All of these are running from the SMB scale-out, which means user VHD, VM, VHDs, and gold VMs are all on the scale-out file servers. The CPU memory RDP load is the same as before. Nothing has changed there. The I/O distribution, totally we have 5,000 users. Doesn't matter if they're PDs or pool VMs, 50,000 IOPS. For pool VMs, we have 4,000 users, which means 40,000 IOPS. The only difference is that pool VMs, because they have the shared parent, there are ways to improve the performance due to the shared parent, right? But PDs, there's no such benefit. So CSV block caching, SSDs, they would reduce the load on the 4,000 pool VMs, but not on the PDs. Another challenge is that PD VMs, the VHD size is quite large. We've done internal self-host deployment. We started with 40 gig per user, wasn't enough. We had to bump it up to 100 gigabytes per user. So that says you need 100 terabytes of shared storage for your 1,000 PD users. Pool VMs, the numbers are really the 80% of the numbers we discussed, just a little bit less, like 20% less, manageable load. Overall network traffic is about the same. Doesn't matter if it's a PD or pool VM, the storage network is heavily loaded. Tweaks and optimization. PD is a challenge in 2012 because it needs so much storage, and the only solution in 2012 was to use SAN deduplication or hardware deduplication to manage that size, 100 terabytes. New in R2 is dedupe for VDI. There's live dedupe for VDI, VHDs on scale-out server, where our preliminary boot focus testing shows that actually the storage can be reduced by 80%. So instead of 100 terabyte, 20 terabyte will be sufficient for handling 1,000 PD users, and boot time would be actually faster, right? We're going to model different workloads, but so far our data is very promising. This is preliminary data, but we're seeing better boot performance and 80% storage reduction. There's a talk on this. I'm not sure if this talk has happened or not. Check it out. Either attend the talk or watch that talk online. They discuss about dedupe and VDI. And they'll share, I think they have a demo actually of the two systems booting side by side, and you'll see that 2012 R2 actually will boot faster than 2012. And it will use less storage. But for 2012, you're stuck with either hardware dedupe or SAN-based deduplication. Last word about GPU. GPU gives you great performance, so if you're considering GPUs, this is a chart, it's a table you can look as an estimation of, well, how much GPU memory do I need to have my VM started? How many screens do I have? And what we tested is ATI Fire Pro, which has got 4 gigs of RAM on a DL585, 70 VMs per ATI Fire Pro. Our test, we put in 2 vGPU cards. We could only host 100 VMs because our hypervisor ran out of memory, but it should be able to do 140 VMs if you had 192 gigs of RAM on your hypervisor. All right, to recap, we talked about the VDI management servers, which is the same no matter what type of deployment you have. The blue font are stuff that don't change. Pool VMs. We need about 35 VDI hosts, 150 users. Same goes for pool VMs with local storage or 5,000 users across SMB. The blue font indicates these values stay the same. What changes is local storage, centralized storage, how much load you put on your storage network. And just to highlight the dedupe feature in R2, the size of the storage can be significantly reduced with 2012 R2 dedupe for VDI. Next, let's explore some test results. So far you have a blueprint of what it takes to do an estimation. Now I'm going to have basically chart data that gives you insight into what does the performance look like. And you can use that as a reference when you're trying to do VDI deployment. So we were hoping to do a 5,000 seat deployment, but we got enough funding to do half the size of that deployment, or about 2,000 seat deployment. And this was built jointly with Dell at Microsoft Engineering Center. And this is what the architecture looks like. It's busy. The slides are available for you guys to look at later on, but this was the first sample, first option we discussed, where hypervisors have CPU and local storage, plenty of RAM to run 150 VMs at 80% CPU. And there's an SMB scale-out that has got EqualLogic behind it for the high availability, the HA storage for PDs. This is pool VM for the user VHD and user settings and user documents. And that same storage is also running all the management server VHDs, which are on the left-hand side. Okay? So 2,000 seat deployment across 14 R720s. These are Win8 x86 running Office 2013, and the login rate is 2,000 users at 60 minutes. So across these 14 R720s, in a period of 1 hour, 2,000 users logged on, which meant 2,000 users in 1 hour went through our broker, SQL Server, and finally were routed to the hypervisors. Hypervisors logged in these users, and within a minute after they logged in, they started running the VSI workload. And this is the final chart that says how well did the system perform. And basically, it's kind of hard to read that little blibbit at the bottom that says VSI max not reached. It means that this system was able to handle 2,000 users without ever the response time becoming problematic for the interactive user. Now let's look at the load on the broker and the SQL Server during that login period. The chart on the right is the load on the broker. It's doing nothing. CPU is about 2%, right? So we threw 2 vCPUs, probably 1 vCPU would have been enough. We threw an 8192, 8 gig on this broker. It uses only 2 gigs, so 6 gigs are free. I'm just putting these numbers up here because we didn't know what to expect, so this is the number started with. But look at the chart. Our conclusion is 1 vCPU, 2 gigs of RAM for the broker, 2 brokers is plenty. The chart on the right is the load on the SQL Server. Okay? So SQL Server, in that 1 hour period, you're seeing a bump, and that bump is about 2.5% CPU. And the I/O, the green is the I/O, and the I/O is just nothing. This transfers 11 IOPS per second, and that's because our database is small. The SQL server has got plenty of memory. It's loaded into memory. Everything is happening from the memory. So 4 vCPUs and 8 gig is a recommendation by the SQL team. That's what we use. You see the load on the SQL server is very small. So there are 2 important points here. One is that typically larger enterprises have a SQL server. And if you think about a VDI deployment for that enterprise, it's easy to rationalize, justify that SQL server could be used for a VDI also. And during the login, the load on the SQL server is small, right? Now, if you had a task worker type scenario that everybody had to log in within 5 minutes, not 1 hour that I have here, that looks like a rectangle. It'll just be squashed. 5 minutes goes up. You'll use about 30, for 2,000 users, use 30% CPU on that SQL server for that 5-minute period. And if you had 5,000 users, right, about 70% CPU. Again, for that brief period, we think the load on the SQL server is quite bearable. So this chart should help you with the SQL server sizing. These are all on the R720s, which is 2 CPUs, two sockets, Xeon E5 2690 CPUs. Now let's look at, remember we have about, in this example, 2,000 in our scale performance testing at Enterprise Engineering Center. We deployed 14 hypervisors, and each load was hosting about 150 VMs. So this is snapshot from one of them, right? The red line is the CPU. It's about 75% for 150 users. The green and blue line are the reads per second and writes per second that are going to the local storage. And you see that the read is about 1,000 IOPS, and disk write is about 750 IOPS. And the disk delay latency is minimal, which means your storage, this storage can handle the load very easily. So how far can we drive a design like this? More VMs, faster login. So the same design, if you drive it to maximum CPU, 100% CPU, 205 users logged on, and the login period was 35 minutes, so about half the 1 hour period we were talking about. This is basically hitting the max of this system. This system, the I/O, the 10 disks, 15K disks, they can't go above 2,000 reads and about 1,500 writes per second. And we see that on the next slide, the VSI max for this environment, which is faster login, more VMs, 100% CPU, is just about 197 users. After that, the response time degrades and users are affected. Another example I'd like to share with you guys is Office 2013 versus Office 2010. And this is relevant when you're sizing your deployment. Office 2013, great experience, the touch, we remote touch, but there's a cost for that greater experience and touch interface. And on the left side, we have Office 2013. We see a VSI max of 197, which means after 197 VMs, user response time degrades. And this system was running 205 users. On the right side, we see Office 2010, that 250 VMs are running, and after 235 users, the response time degrades. So the impact of Office 2013 is about 20% more CPU. You should bear in mind when you're sizing your deployment, you should consider the more CPU demand of Office 2013. HA broker and provisioning. So two charts, 2 bar graphs. On the left-hand side, we have 20 connections coming concurrently. On the right-hand side, we have 50 connections coming concurrently. The blue tall line is a single broker using local storage, local database, Windows database. The red is the SQL backend. And you see that by just having 2 brokers, we're able to do in about 2 seconds, we're able to handle 50 concurrent connections and target those connections to the appropriate final VM. And adding more broker doesn't really help much because SQL Server is doing the real work. For less number of connections per second, the chart on the left-hand side describes how long we take to route the user. It's an example of 20 and 50. And the collection size is 1,000. So collection is 1,000. Some VMs have a disconnected session, some don't. These two charts show concurrent connections coming at 20 and 50 and what the response time looks like at the broker. Remember I mentioned there's an option to increase the number of concurrent VMs, number of VMs we create concurrently or update patch concurrently. In 2012, we limited it to 5, but in 2012 R2, we've tested it to 20. And this is how significantly it will reduce the time to provision or update your pool VMs. For example, it takes 2 hours if the concurrency value is at 5 with 2012. It'll take about 1 hour, half that time, if the value is set to 20. IOPS due to VSI workload, you remember I said about 10 IOPS. This is just for your reference. If you want to see the details about where we got this number, this is where you can look at and see that indeed the VSI workload generates about 10 IOPS on average per user. I want to talk about VDI host memory versus storage. Okay? So here's a hypervisor that the green line is showing users logging in. So partition number is increasing, is the green line. And as the partition number increases, the memory available, which is the black line, is going down. All right? And we eventually reach a maximum number of partitions, which is 228. Okay? Initially, you look at the pink and blue lines, and that's the reads and writes per second, and they're all about the same. But what happens is suddenly they jump. And the question is, what goes on? And this is about host memory versus storage. So what happens is that our hypervisor here doesn't have enough memory, and it's using dynamic memory to host more and more VMs. And dynamic memory, what it'll do is it will squeeze on the upper chart. You see it's squeezing memory out of guest VMs, which means the page files are flushing. So what happens is that the guest VM, when Windows is looking for stuff, it has to go to disk. The point here is that if you're estimating the memory necessary for your hypervisor and you count on dynamic memory, you should bear in mind that by leveraging dynamic memory, your storage has to be able to take the extra load that the guest VMs will put on storage when you reach the maximum memory on the hypervisor. Okay? Overcommitting means more IOPS on storage. CSV caching and VDI. So remember that I said, there's a cost of using centralized storage. The network becomes more complicated. Your data center is more complex. Why would you do that? Well, it's because you take benefit of CSV caching. This chart shows 40 pool VMs starting from the off state. CSV cache is set up to 1 gig, so it's a single collection. And we're seeing a benefit of 75% reduction in the read IOPS because CSV cache brings the memory of the gold parent VM. Those are the hot blocks and keeps it in memory. So the top line is the cluster I/O reads. And the red line says the cluster cache that was, the reads from the clustering that was satisfied. And the green is the reads which were not satisfied and went to the disk. You see the tremendous difference between what's satisfied from memory versus what goes to the disk. That's how we reduce the demand on your disk. In this chart, it's the VSI workload. So this is not the boot time. This is another experiment where the normal workload is running the VSI medium workload. And on the left side, we have the CSV block cache enabled. And the right side, we don't have CSV block caching enabled. And you can see with the yellow and green line that CSV cache is reducing. It's satisfying the reads, and it's reducing the load on your storage. Whereas on the right-hand side, the load on storage, the blue and green, are much higher. The SMB load, load on the network due to the SMB storage. So remember I said that by having centralized storage running all the VMs from the centralized storage, you put a lot more load on the network. This is an example from one of the SMB clients. So this is one of the hypervisors. All the VMs are running from the SMB scale-out server. And we see the load it puts on the traffic to get the VHDs, right? So the write request is about 750 IOPS. Read request is about 2,100. Write bytes per second is 25 megabytes per second. Read bytes per second is 60 megabytes per second. You aggregate this for 5,000, you see the load on your network, data center storage network. And finally, a real geeky slide here. It's about vGPU and memory. So the vGPU system, the way it works is that we create vGPU DX processes on the parent partition to help with the vGPU workload in guest VM. If you look at the chart on the left-hand side, what you're seeing is that we have a hypervisor that has about 129 gig of RAM. And we have an ATI card that has 4 gigs of RAM. And users are logging in, and the partition count is increasing, which is the red line. And we get about 82 VMs. And the kind of dirty green line in the middle is the system memory. It's going down as more users log in, but it never hits zero. We have about 20 or so, 20, 30 gig around here. And the GPU memory, which is 4 gigs, starts about 1 gig in this snapshot I have. And eventually, when we have 82 users, there's no more GPU memory left. We can't create any more VMs. And when we hit that point, all the users who are logged on, they have a great experience. It's just that the next user who wants to log in, they can't log in because there's not enough VMs. Key point is that all the users who have already logged on have great experience, no effect on their experience. The slide on the right is the same hypervisor which has only 129 gigs of memory. And we have 2 ATI cards plugged in, right? And what happens here is that as the number of sessions, number of VMs increase, eventually the hypervisor runs out of memory. And because we have processes in the parent partition running DX to mirror what the guest VMs do, those applications are starting to be swapped to the disk. When that happens, all the VMs are affected. So the user experience across all users who had logged in and had great experience, once the hypervisor runs out of memory, the user experience in these VMs across the board is affected. So when you're thinking about vGPU, it's really important to leave extra memory for the hypervisor, or as unlike previously that we could just not create a new VM and user experience is not affected for the users who are logged on, here user experience across the board will suffer. DM will do its job, right? VMs will be created, right? But user experience across the VMs that had a good GPU response will go down. So keep an eye on, if you have a vGPU deployment, what the memory, free memory is on the hypervisor. As it gets close to zero and the dynamic memory kicks in, it will affect all the vGPU workloads. Well, our inbox, we have a PowerShell scripting layer that we've tested to 5,000 seats. We've benchmarked a 2,000 seat deployment. We're working on a 5,000 seat deployment, including PD VMs. And we have an inbox admin UI that is designed for 500 seats. So if you're considering a large deployment, it's a management layer, an admin workflow layer should be built on top of a PowerShell layer that we have tested to 5,000 seats. We don't think 5,000 seat is the limit. Just our test infrastructure could handle 5,000 seats. And we're going to benchmark more than 5,000 seats, hopefully with R2. Other interesting talks or downloads to check out. I've enumerated these. If you go to the slide, my slides, you can just pull this down. There's a remote desktop service team blog that's worth checking. We try to blog more than published white papers these days. These are standard stuff squeezed into my session. Probably you've seen these before. And some encouragement to take a snap and evaluate the session for free gifts and so forth. Thank you, and if you have any questions, I'm here.